Today we're going to move into the realm of digital information and talk about binary systems and how those are utilized in the computer industry. As humans, we have been trained up on the decimal number system, or base 10. We deal with that through the use of the numbers 0 through 9. And in that decimal system, we have certain positive and negative signs that we attribute to determine the magnitude of a number. And we also have the ability to work with decimal fractions. That works well for us for numbers, but as humans, when we read something, we have developed obviously a text-based or letter-based system for recording information. Contrasting that, on the computer side of the house, computers use only two numbers. They are a base 2 system called a binary system. They also have the ability to have different signs and magnitudes, as well as fractions and floating point type operations. Text or letters, however, become a little bit more of a problem. Because computers can only work in binary numbers of ones and zeros, we have to come up with a code, an ASCII code, what we call a conversion set, that translates characters into numbers. Well, let's look at binary. Why binary? How was binary chosen? Well, essentially, you have to remember that because computers are electronic and based off of electricity, they function through the use or the measurement of the presence or absence of electricity to provide some distinct value. Now, if we were trying to match our normal decimal base 10 system that we're used to in electronics, that would require that we had 10 distinct and reliable voltage levels for each digit 0 through 9. That simply just isn't feasible in terms of reliability or financial constraints. Therefore, everything in a computer is stored in ones and zeros. Doesn't matter whether it's a number value or text or a picture, a sound, a video, everything is converted to binary. A little refresher. Early on we talked in the class about transistors, how transistors are kind of the fundamental component of electronic processing, and they basically function as a switch. They allow current to either flow when they're on or not to flow when they're off. So we have two steady states depending on whether there is voltage or is not, or it could be a certain specific level of voltage, like 5 volts could be high and 3 volts could be low. That would accomplish the same thing. Just a refresher again, there's lots of transistors in a modern processor. The Intel 15-core Ivy Bridge has over 4 billion transistors inside one little chip. And those transistors can change their states from on and off in a billionth of a second. So as we represent binary numbers, it's really pretty simple. There's just two. It's a 0 and a 1. However, keep in mind that we can also represent those same values through the use of words in terms of symbols such as false and true. And we'll get into this when we start getting into programming, in evaluating expressions as to whether they are true or false. You can also in electronics use the symbols of low and high, and sometimes the words of simply on and off are used. Now, binary is not really a new concept. It's been around for some time. A perfect example of it would be the old Morse code system of sending telegraph messages over the wire. In this particular binary coding scheme, we're using not ones and zeros, but dots and dashes, or what translated into short and long tones on a telegraph wire. You'll note in the chart that the most common letters in the alphabet, the A's and the E's and the N's, were all made up of very short characters because they occurred the most often, and to facilitate transmission speed, the designers of Morse code figured that would make things work a lot faster. So when we look at the decimal base 10 system, which is what we use on a daily basis, and we narrow our focus only to the non-negatives or positive, if you prefer, numbers, just to keep things simple. We call it a base 10 system because it has 10 digits, and those digits are 0 through 9. This is also a positional system, where the actual position of the number gives the power of the base. And we have an example here, 3,845. The 3 is in the thousandth position, or 3 times 10 to the third. The 8 is in the hundredths position. The 4 in the tens, and the 5 is in the ones position. As we go through this, we're going to be looking at your exponents. So keep in mind the zero exponent rule here, which is that anything raised to the 0 power is automatically changed into a 1. Therefore, 10 to the 0 becomes 1. 5 times 1 becomes 5. Now, binary, also focusing our efforts only on positive, not the more complicated negative and fraction end of things, is a base 2 system. We use zeros and ones, and this is where the term bits originated from, because it's a binary digit. So only 2. It's also a positional system. This one is a little bit trickier to get through your head. Not that it's harder. It's the same exact concept. It's just not what you're used to seeing. So let's take an example. Here's a binary number, 1101. It's positionally based. So it's 1 times 2 to the third, 1 times 2 to the second. This is the 0, so 0 is 0 times 2 to the first. And remember that anytime you multiply something times 0, it's 0 and it goes away. So in reality, it doesn't even have to be represented here. And then 1 times 2 to the 0 is just 1. So point here is the positionally based system. Here is a little chart of the different powers of 2, and it would be extremely helpful if you would memorize this if you're going to work very much in the computer industry. It just makes things a lot simpler, because the more you get to understand and be familiar with this chart here, you will be able to quickly and competently calculate a lot of different things in the computer world. You'll notice that they're just a doubling of 2's, 2 to 4 to 8, 16, 32, and so on down the road. Example, in the base 2 system, the important things, the symbols are zeros and ones, and the place values are going to go from the smallest to the largest. So here's the decimal point. It is possible to do fractions, and it is possible to do negative numbers, but we're going to focus over here. Again, here are the numbers that you want to remember from a place value standpoint. 1, 2, 4, 8, 16, 32, 64, 128, 256, and so on. So for an example, let's change the base number, or the binary number of this to a decimal number. We take the first one, and it becomes 1 times 1, because it's in this place value. Take the second one, it becomes 1 times 2, which equals 2. The third one is a 0, so it's going to obviously have no value. The next one will have no value. This one will be 16, because it's here. And then the final one will have a value, of course, of 32. So you add all those up, and you get 51. That's the decimal number that is converted from this binary number. Now go in the opposite direction. If you have a decimal number and you want to convert it to a binary number, totally different concept. We're going to use a strategy here of dividing by 2 and paying attention to where the remainders are. So let's take the number 47. We divide 47 by 2. We get 23 with a remainder of 1. Take what was left over, 23, divide it by 2. We get 11 with a remainder of 1. Take the 11, divide it by 2. We get 5 with a remainder of 1. 5 divided by 2, 4 with a remainder of 1. 2 divided by 2 is 1, and there's no remainder. Finally, 1 divided by 2 is 0 with a remainder of 1. Therefore, you take these numbers, and the order is important, so that they become laid out like that, and that then is the number 47. That is one method of doing it. So we're talking about conversions from external, which is the human perspective of decimal base 10 numbers such as 25 or letters A, and how do we represent that internally within the computer. So the conversion of decimal 25 to binary 11001, or the letter A to some binary representation. Let's take another quick look here at a different method of achieving things. We have a simple algorithm using the positional scheme. This is like the one we looked at before. Simply taking each of the individual numbers and their position within the order, so that we have 2 to the 4th plus 2 to the 3rd plus 2 to the 0th, which is 16, plus 8 plus 1, which is 25. Now the binary addition is something that you need to at least get a feel for here, how this works. This truth table gives you a pretty good idea. If you take a 0 and add a 0, you end up with a 0. If you take a 1 and add it to a 0, you have a 1. And if you take a 1 and add it to a 1, you get a 0, but if there's a carry bit of 1. So let's do an example down here. We take the number 53 and add it to 45 in binary. So we have the 1 plus the 1 is 0, right? 1 and 1 is 0, but there's a carry, so we put the carry up here. So now we add down the column. We have a 1 and a 0. 1 and a 0 is a 1, plus another 0. 1 and a 0, so it's 1, okay? Then we have a 1 and a 1, which is back to a 0 with another carry bit. We have the 1 and the 1 is a 0, another carry bit, and so on until we get the full binary answer, which translates to a decimal of 98. Now realistically, we're not going to be doing much addition in binary. I would recommend that you look at the Windows calculator or on your Mac and see if it also has a ability to shift into the programmer's mode and calculate these things using a calculator. But it is important that you can at least do some basic conversions to be successful here in the class and on the test. Now I want to remind you too that we have special powers of 2 that we have designated as the kilo, mega, giga, and tera bytes typically. And those are the values 2 to the 10, 20, 30, and 40. These are the more precise values. We took the approximations when we were talking about megapixels in the talking about monitors and how video is displayed, but these are the actual real values. Just as a practical exercise here, what is the most memory, RAM, that a 32-bit processor can access? If you have a Windows operating system and it's running the 32-bit version of that particular OS, there is a limitation to how much memory it can address, and therefore how much is, I mean, you could easily waste your money if I put too much memory in there that the processor cannot even address. So 32 bits would be written out like this in binary. So what does that equal to in decimal? Well, if there's 32 bits, then it's simply 2 to the 32nd, which is this number, which is a total of 4 gigabytes. Therefore, a 32-bit processor can only manage 4 gigabytes of RAM. If you have a 32-bit system and you stick 8 gig of RAM in it, you're wasting your money. It can only see the first 4. One final reminder here is that 8 bits are called a byte. 4 bits happen to be called a nibble, so you can't say that programmers don't have a sense of humor. Now, there are some other peculiar base systems that we use in computers, as if binary wasn't awkward enough to work with. We also use the base 8 system, which is called octal, and we use the base 16 system, which is called hexadecimal. Octal numbers, 8, so we have 8 digits, 0 through 7, not so many, so that a number made up of an octal is not going to have quite so many digits as a binary, so it's a little bit easier to work from, easier to convert. This is typically only used in areas where they have to represent data internally in programs. One place you'll see it quite a bit, though, is in networking. If you are planning to do much work in the networking side of the house, you need to understand that IP addresses and subnet masks are made up of what we call octets. A typical example here, 192.168.0.114 with a subnet mask of 222.55.0. These, if you recall, in our discussion on IP addresses, being octets, only having 8 possible digits, are going to be in a range of value from 0 to 255. So converting from octal to binary is really quite simple. You just take each octal digit and you convert it to a 3-bit binary number. So the octal value of 536, you take the 5, you convert that into a binary 5, the 3 into a binary 3, and the 6 into a binary 6. And that's how it's represented. Going the other way is just the opposite. You take a string of binary numbers, you break it into groups of 3. So this group of 3 is, let's start at the other end here. This group of 3 is this one, and this group of 3, and so on. We just lost the leading 0 on it. And then you can do the math, and it turns out to be that number. And finally, hexadecimal. This one you're going to want to make sure you understand, because this is going to come up again, especially as we get into digital information in the context of colors and video and images in particular. So hexadecimal is a base 16. There are 16 digits. Now you might think, how can there be 16 digits? Well, we simply, when we get to the 9, we start adding alphabet letters. There is precedence for this in your common everyday experience. If you think about a deck of cards, a deck of cards has the ace, they omit the 0, but they have the ace, the 9, they don't, and they have a 10, but then they have a jack, a queen, and a king. So there are, common uses of this sort of thing. It's just you have to get used to thinking about after 9, you still have some additional letters to work with. So conversions from hexadecimal to binary, it's just the same as octal, only you use 4 bits per digit instead of 3. So here is an example of a hex value, 98C3. You take the first digit, you convert it, the 9 into a binary 9, the 8 into a binary 8, and so on. And then converting from the binary to the hexadecimal, same thing, only in groups of 4. And then you convert. This is a decimal 3, or digit would be a 3, this would be a 4, this is an E, and that's a B. So that covers basic numbers. Let's diverge a little bit here and talk about letters or characters, as we prefer to call them in the computer industry. There's a code out there that was developed by the American Standard Code, the standard industry. It was called the ASCII code, and it's a specific set of characters. We also often call it a plain text representation. The original set of characters was based off of a 7-bit character code, and every single bit represents a very unique character. Later, IBM kind of extended this into an 8-bit character set, which went all the way up to 256 characters. And be aware that there are several different standards of the extended ASCII character set. International version, Microsoft Windows has their own Latin 1 version, and those things are typically available in programs like Microsoft Word. So there's an ASCII table that's at this website that I would recommend that you utilize for your homework assignments. But let's take a look at what this thing looks like. So the first group of the ASCII control characters from 0 to 31 are not printable. Okay, these were control codes that were used to control external peripherals, notably printers and communications gear. These are still in use, and there's still a few of them that are particularly worth knowing, notably the printing and the things that also work on your screen. Things like a carriage return down here at the bottom, number 13, decimal 13. The carriage return takes from the end of the line and takes your cursor back to the beginning. If you couple that with a line feed, you get the effect of moving to the next line, like an old typewriter. You pull the lever, it does a line feed, and you drag it all the way back and to the beginning. Form feeds, where you eject a new form out of a printer, and so on. So those are non-printable character codes. The next set starts at the value of 32 and goes on down to 127. These are the 7-bit characters, and this is where all the ones that are on your keyboard can be found. So these are the printable ones. You have a space bar, you have the exclamation mark, ampersand, asterisk, comma, and as it goes down in value from decimal to the larger numbers, you get into the letters. For the uppercase letters, and then even farther down you'll find the lowercase letters. The last bit is the 8th bit, which represents the characters codes from 128 to 255, are mostly the odd ones, the odd ones here that are really rarely used, that you're welcome to take a look at those. And then finally, we'll wrap up our discussion of ASCII with what was not so boring. Back in the beginning, when all we had were line printers that printed the standard characters on a keyboard, people still had the opportunity of having a little bit of fun on the printers and figured out ways to do ASCII art. As you can see, Snoopy and Calvin, the cat in the hat, and a guitar, and many, many more things were done on the printers. That pretty much wraps up our discussion on the ASCII art and the ASCII codes and the conversions. So let's go through a little practical exercise here, and you want to use your handy ASCII chart to do this. Here's being asked to convert the ASCII text of Groucho to binary. So we go to our chart and we find the uppercase G, and we find that the binary representation for that is this sequence of zeros and ones. The R lowercase is this, and so on down through. So a very simple process. You just have to pay attention to which column you're reading as you do the conversions. Going the other direction from binary to ASCII, here's the question: what movie title is represented in binary as this big sequence of binary numbers? So we take the first block of numbers, we put it down here. You can do it this way. You can do the positional power, 2 to the 6th, 2 to the 4th, plus 2 to the 1st, plus 2 to the 0. Convert those to their binary or their decimal values, add them up. You get the value of 83. You check in the chart. Decimal 83 is a capital S. If you go through each one of those, lowercase t, A, R, and don't forget, you have to specifically represent a space character. It doesn't appear there magically. And then you follow it on out, you end up with the title of the movie being Star Wars. I believe that will conclude this session on binary. I hope your brain is still intact.